Okay, everyone see my images and do you hearing me or us our sound? Okay. Just talk about our process of the discourse. Okay, I talk with the chief of our department. Okay, and according to discourse, I will not make a midterm exam. Okay, and I have just only final exam at the end of the semester, and I will give some assignments. You have to prepare a presentation about infrastructure. There is no midterm, okay? We have just only final exam at the end of the semester. We have one assignment, water distribution. Any question? Water. I'm not sure. Question. Let's start with water, my friend. Okay. Well hydraulics. What is the well? The first. This is the important problem. And in our water engineering, groundwater, or below the water table, we have a country. There are lots of groundwater valves to supply the clean water. Okay, it's very important for us, and we have to we have to examine the hydraulics of these valves, this groundwater, as a civil engineer, as a water engineer. Let's talk about the groundwater zone first, okay? And the unsaturated zone, you see that, often called the vadose zone, is the portion of the subsurface above the water level. This zone is a storage of water, plant nutrients, and other substances, a zone of the transmission of water and other substances, a zone of the natural and human-induced activity. Okay, and this is the unsaturated zone. That means there is no saturation. Okay, the water transmits this level, this zone, to the saturated zone. Saturated zone, you see that this is the unsaturated zone, which means there is no water table. The below limit of the unsaturated zone shows the water table, and the saturated zone, in which all the pores and the rock fractures are filled with water, underlies the unsaturated zone. Okay, these are very important, my friend. Okay, do not forget this zone. The top of the unsaturated zone is called the water table, and the water table may be located only a foot below the ground surface, or it can be sit hundreds of feet down. Okay, you see that when the precipitation drops to the surface, the first it faces the unsaturated zone or vadose zone. Okay, this is the seepage or infiltration. Unsaturated zone arrives to the water table. Water. Okay, it's important. Okay, it's important. Although the groundwater exists everywhere under the ground, some parts of the saturated zone contain more water than others. What does it mean? Which means that just imagine the saturated zone. In everywhere in the saturated zone does not contain the same amount of the water. Some part of the saturated zone amount highly content with the water. Some of them is the lowly content of the water. Okay. And important thing is, what is aquifer? Aquifer, maybe you can heard that. Aquifer is very important term as. If you know what the aquifer means, okay, you can answer the groundwater stuff, the most of the groundwater stuff. An aquifer is an underground formation of permeable rock and loose material that serves as a storage reservoir for large volumes of groundwater when tapped by well. Okay, actually the aquifer is the pore structures, and you see that is the pores, and that is the aquifer as a sponge. You can imagine the aquifer is the sponge, and you see that is the low permeable medium, and that is the high permeable medium, because we have a great diameter of the particle, maybe gravel, and that is actually the high amount of the sand. If we remember this material, and for the sand material, sand particle between 0.05 and 2 millimeter diameter, silt 0.02 and 0.05 millimeter diameter, and the clay less than 0.002 millimeter diameter. Okay, and from the 2 millimeter we have a pebble or gravel. And what kind of aquifers do we have? In generally, we have three type of aquifer, and mostly we can consider two type of aquifer. Okay, the first one is unconfined aquifer, and the other one is confined aquifer. And just middle of this we have a perch aquifer. Okay, but generally we can use the confined and unconfined aquifer, and we can call the unconfined aquifer is an open aquifer, and the confined aquifer is a closed aquifer. Let's meet this kind of aquifer, my friend. Okay, that is the unconfined aquifer. Is, you see that the unconfined aquifer is bounded from the below with the confining unit, which means unpermeable layer, and unconfined aquifer is bounded from the below with the water table. There is no confining unit. Okay, on the other hand, if we have a confined aquifer, that means confined aquifer, it's bounded from the below and the above with the impermeable layer or confining unit. Okay, it's important that, which means you can imagine unconfined aquifer just work like a pressure water. Okay, pressured water, and that means there is no boundary with the below side. The surface can rise. Water flows downwards small spaces or fractures to fill gaps in the rock or sediment. Okay, and the position of water table may vary due to the seasonal precipitation change in the groundwater consumption. And confined aquifer, an aquifer bounded above and below by impermeable layer or confining units, aquifers or aquiculate of a lower permeability than that aquifer itself. Okay, as I said before, for the confined aquifer is bounded below and above with the unpermeable layer. And one of the aquifer is the perch aquifer. Perch aquifer is a small water body which is situated in unsaturated zone of a soil above water ground table or main unconfined aquifer. Okay, you can imagine the perch water bodies. You see that aquifers can also receive water from surface waters like lakes and the rivers. When the aquifer is full of water, the water table meets the surface of the ground, and the water stored in the aquifer can appear at the land surface as a spring or sea. Just remember the season, my friend. For the spring or winter season, when the groundwater table arrives to the surface or increase the water level, you can see the groundwater table, okay? It reached to the almost the surface of the land. Water infiltrates faster into soil that are mostly sand than into those that are mostly clay or silt, as we know that. Almost no water filters into paved areas. Rain that cannot be absorbed into the ground collects on the surface, forming runoff stream. Okay, and when the soil is completely saturated, from the other perspective, additional water, extra water, moves slowly down through the unsaturated zone, and the saturated zone replenishing the area, recharging to the groundwater. Okay? If the evaporation occurs when water from such surfaces as ocean, rivers, or an ice is converted to the vapor. Evaporation, together with the transpiration we call the evapotranspiration from plants, rises above the Earth's surface, condenses, forms clouds. The percolation, groundwater most probably reach to the lakes or ocean or the river. From the evaporation, it turns back to the atmosphere, and then evapotranspiration with the plants or grass, and then with the precipitation to the surface. After this step, we have some terms related to the groundwater hydrology, okay? An aquitard, aquicloud, and aquefuge. What is the aquitard? An aquitard is also a saturated formation. It permits to water through, but it does not yield water in sufficient quantity as much as aquifer does. Because of their partly permeable nature, the impermeable geological formation which is neither porous nor permeable, which means it cannot store water in it at the same time. It cannot permit water through, it's such a compact rock. Okay? And you see that. And this is water table, and that means that is the unconfined aquifer, that is the confined or artesian aquifer. In other words, we can define the confined aquifer as an artesian aquifer, aquitard, confining layer, you see that? Before we start the terminology of the well hydraulics, okay, I have a video about these terminology, these term of the groundwater resources, okay?
Of the whole water cycle.
Can you see and hear the video, my friend? We have just that is
wells underground and many layers of rock, sand, clay, and gravel deep under the surface of the earth. Aquifers are just those layers that hold water and allow water to pass through them. The layers that don't hold water, don't let water pass through, are called aquitards. This model can show us something very important about water on our planet. It's a closed system. Every bit of water we have now is water we've always had. There's no such thing as new water. The water we'll drink today is the cycling itself, and we pull it up through wells and use the topsoil into the aquifers and recharges them. So we have recharge and discharge of the aquifers as part of this whole cycle. We see that surface water and aquifer water are really all the same water, constantly recycling, made of different material, a little color to it, so that you can see the movement more dramatically. I think you're going to notice two things. One is that water moves at very different speeds in different aquifers. The other observation is that the water all moves in the same direction. This, in both respects, the model is reflecting Kirk County. This is the high pressure side, this is the demonstration. It always moves from a place of higher pressure to a place of lower pressure. A big difference between the model and the aquifer is this stone aquifer, this rock aquifer. In the model, it's on the bottom. In real life in Kirk County, we've grouped our aquifers together up at the top and furnish and support the Guadalupe River. The Guadalupe River in this county is a source of. Now this drains north and west of Edward and some little pools, but very rich in water for us. Droughts and floods are very common in our region, even do damage with the heavy water. When the surface, we can see it, but we have to remember to keep enough water in reserve. Water fills a well because the pressure in the aquifer is higher than the pressure in the well bore. In fact, from the model, just as that pipe and the water rushes in to take its place. When we pump our well, we may notice that the water level is also in the same bottom aquifer in the model. When I pump well 1, you noticed that the water dropped in well 7. This is called the interference of wells. The well with the biggest pump, that's like headwaters or conservation districts, is to water, is based on in Kirk County, but moves in from around us. In the 1970s, and have excess of what is actually demanded by the citizens of Kerrville, because they're not doing any outside watering, to be drawn back up and used to meet the demand. That fast-moving karst aquifer that's on top, and which way is it going? Natural resource. Thank you.
Some kind of stuff is very important for us. Just remember the video and just remember that we talk about it, okay? Do not forget this definition. According to this course, the next term is the terminology of the well hydraulics. How can we design the well? How can we use the groundwater? And we need a well, and we have to know the well hydraulics. Groundwater withdrawal from aquifer are important to meet water demand. In most of the countries all over the world, we can use the groundwater. Therefore, we need to understand the well hydraulics to design a pumping strategy to get adequate amount of water. Okay, you see that. That is the groundwater. And when we put the well to discharge the water, discharge the groundwater, okay, discharge the groundwater. If you supply the water from the ground surfaces, drop in the water table from previous static water tables called as a drawdown, which means that if we supply the water from the well, the water comes through the well and the water level can start to decrease. Okay, we define that this decrease is a drawdown. And what is the cone of depression? Represent the water table. Just remember the video. During the drawdown of a water table with the help of the well through the aquifer, which means that for us we call the capital R is the maximum distance up to the effect of drawdown is detected. Okay, and you see that that one is the radius of the influence. Actually, that is the radius of the cone of depression. Initially, drawdown is not constant at the beginning. After a while, there is no change in drawdown. The position of water table may vary due to the seasonal precipitation and the change in the groundwater consumption. If we pump a single well in an idealized confined aquifer, my friend, actually we can analyze this well hydraulics considering the confined aquifer and the unconfined aquifer. And you see that is the unconfined aquifer. It's bounded from the below and the above with the confining unit. If we analyze the single well in idealized confined aquifer, we put the well and we start to supply the water, and the water level start to decrease, and that is drawdown, that is cone of depression. Okay, and in the aquifer, in the confined aquifer, water, in case you supply the water, water comes to the well around this well. If we consider the unconfined aquifer with the single well, idealized unconfined aquifer, you see that is the unconfined aquifer is just only bounded for the below. That is the confining unit. That is the cone of depression, drawdown. We are discharging the water. Let's talk about the theoretical background of the groundwater. If you remember the groundwater hydraulics, groundwater flow is generally laminar flow, which means that the flow is very slow, and we have a layered flow. Okay, layered flow. Small groundwater has a small velocity with the layered flow. Line of the groundwater flow. You see that. Just remember the Darcy law, Darcy's example, Darcy's law, something like that. That means delta H has different soil types. Let's focus on that. For the sand particle, between the grain size is 4 mm and 8 mm, K is approximately 0.0025 meter per second. If the sand material diameter is between 2 mm and 4 mm, and the K is approximately between 0.025 and 0.030. Okay, and for the gravel is very high, zero. Just remember the geotechnical lesson or material building material lesson. We have a sieve analysis, and we can find the effective diameter of the particles right in size as high as 10 for heterogeneous sand, and the uniformity coefficient can be found d60 over d10. In case you know, calculated like that to the hydraulic conductivity. How can we supply the water from the ground sources? First of all, we design the well. What kind of well do we have? We have dug wells and the drill wells. Dug wells are holes in the ground dug by shovel and the backhoe. Historically, a duck well was excavated below the groundwater table until incoming water exceeded the digger's bailing range. And the drilled wells consist of a hole bored into the ground with the upper part being lined with the chasing. Okay? You see that this is the drilled well with the if we focus on the well screen, remember that is the well. If we talk about the bottom and the side, we have two ways to come through the well. The one is bottom of the well. The other way is the side of the well. That first example shows the water comes through the well with bottom and the side. That one is only bottom, that one is the side. Okay? And why do we do that? Because we have to calculate the cross-sectional area that connect with the groundwater. Okay? If we talk with the bottom and the side, that one is the bottom area, PD squared over 4. That one is the sides area, P times D times H. D is the diameter of this area. The H is the height of the water, okay, height of the groundwater. So if the water is taken from bottom of the well, A is that one. If water comes from sides only, that is the area. And if the water is both, if you sublime allowable velocity according to square root k maximum velocity, multiply the area. But before we start the theoretical, you see that? Yeah, let's talk about the unconfined aquifer. But before we start the theoretical background of the unconfined aquifer, my friend, if you want to have a break, we can have a break. We can take a break. If you need to have a break, my friend, can you hear me? Okay, let's have a 10 minutes break, my friend. Let's have a 10 minutes break, and then we can meet just 8.15. Okay, after 12 minutes we can meet and we can continue from the unconfined aquifer. Okay.
Doctor?
Yeah, I'm listening too. Abdulaziz, I remember. Yes. Yes, Abdulaziz.
Yes, Doctor. Last week you told me to come in at the university. I came at the university on Thursday, but I didn't find you today.
I'm not hearing you. Okay.
Now, Doctor, you are
Your
hearing
sound
me
is
now.
very discreet. I cannot hear you, Abdulaziz.
Yes, Doctor. Now, do you hear me now, Doctor?
Thursday, inshallah, I will.
3 o'clock or not?
At the end of the course, we can pumping a flow, and if we use the Darcy formula, at the end of the formula, we can obtain the pumping flow rate as a Q is equal to P times K H square over small h square over ln R over R. Okay, That is the unconfined aquifer formula, okay? That is the theoretical formula. What is the capital H? The capital H is the static water level. The H is the water level inside the well, okay? And the capital R is the radius of influence. R is the well radius, the water drawn. S plus H is equal to that one, 2PRH. As I said before, that is the side area of the cylinder, side area of the valve, 2PR, or P times D multiply H, okay? And if you remember to the Sicard allowable maximum hydraulic gradient from the maximum velocity, that one, my friend, and that one is the Q maximum 2 times P times R times H. That one is the square root K, that over 15. Maybe, which means that is constant according to these parameters, but that can be changed, okay? If you want to supply, it can be changed. But we have to analyze, we have to determine both of this discharge, okay? And we called Q1 is the theoretical formula, Q2 is the maximum allowable discharge formula, and if we get the combination of these two discharge, we get the optimum discharge, okay? That means the optimum discharge, that means you can supply the optimum amount of water from a valve using this optimum discharge, okay? So we can say Q1 and Q2 are solved simultaneously to find optimum Q that can be drawn from a valve without any damage to the aquifer. What kind of damage we can talk about it? Maybe particle erosion inside the medium, inside the particle, okay? If we supply more amount of water, so the particles move, stop. You see that? Similarly, we just only two impervious layer from the above and the below, and we call the M. M is the aquifer thickness, okay? So pumping flow rate can be calculated like that: 2 times pi times K over M, H over Ln L R over R. That is the confined aquifer formula. That one is the maximum allowable withdrawal from a valve with the confined aquifer. So if we work simultaneously with the Q1 and Q2, we get the Q optimum. So my friend, if we summarize these aquifer formula, for the unconfined aquifer, this is our original formula. For the confined aquifer, radius of the influence and the draw. So the outer surface area of the valve we call the P times D times H, flow called the maximum allowable velocity, passing through the filter holes, and the velocity of faster passing through the filter holes according to particle size of filter zone. In general, if the effective particle diameter D50 is less than 0.5 millimeter, we call the approximate velocity is 1 millimeter per second. And D50 is greater than 1 millimeter, and the velocity is almost 2 millimeter per second. And D50 is less than 0.25 millimeter, and the velocity approximately 0.5 millimeter per second. Okay? By using sieve analysis, the diameter of filter pack is just a After determining the outer diameter of filter pack, size of the particles in the inner layers are determined by assuming the particle size in each layer is 4 times larger than the outer layer. You see that, which means from the DIN standard, you see that this can be changed according to these standards, and it can be 4 times larger when we compare the inner layer and the outer layer. And that is the well with the filter pack just around the well, and we have a sand gravel filter layer. You see that is the pump. We put the groundwater hydraulics, my friend. One more topic about this groundwater hydraulics. This is the different water inlet K, h squared over h squared over 2r meter cube per second. L is the length of the drainage gallery, K is the hydraulic conductivity, K is the static water level, H is the water level inside the gallery. If we have a dual side drainage galleries, Q is equal to L times K, h squared over h squared over r. And one more different resources. If water table has a gradient flowing groundwater, you see that is the drainage system. Okay, that is the drainage pipes, drainage layers. Drainage from the confined aquifer, single site drainage, Q is equal to M times L times K, that one is over R. Dual side, 2 times M times L over K. Drainage system, we put the drainage pipe, and that is the filter pack. Okay, that is the drainage galleries and different resource from the groundwater. Any question, my friend, for the about these rules, these formulas? Which parameter these formulas? I share my email. Just if I'm listening you.
Oh yes, doctor. About this course, did you divide the grades and course syllables or like that system?
Sorry for the Abdulaziz. I shared my mail, okay? erdal.keskin@altınbaş.edu.tr. You can just mail me, and as I said before, I have one presentation and one final exam. I give the grades according to this presentation and did the final exam. The presentation or assignment or homework, maybe you can say it, you can consider this is this kind of a midterm, and you will prepare an assignment and presentation, and I will give a grade. Okay?
Doctor, but the final exam, because a lot of students, they are rejection of the visa, and they have a lot of problem. So how can we divide it? Like make it online final exam, making paper and solving again, uploading in the
face to face. But I will ask for you, for the chief of the yes.
Doctor, but we have another course like with the doctor. He divided into a presentation like and the midterm, and conclude some articles in one paper as a final exam, because he know us. We have a lot of problem, and like now rejection visa, and like in corona, and a lot of things, and he appreciate in this situation. About this, doctor, at the same Altınbaş University, you have do you have a problem like that?
Abdulaziz, I understand you, but when I asked you last week, it's
we have a course on like a new course. I believe.
Inshallah, Thursday I will ask. Starting with the 8.30 and to the maybe you can sources. No, how can we transmit the water? That is the big problem for us, okay? Yes, we we find the sources, let's say groundwater sources, and how can we transmit the water? Transmit the water to the cities or school. I'm not opening that. Solve the if we finish the water transfer resources or about the irrigation. You see that of the water transfer. This is important, my friend. What is the functionality of this reservoir? It means this we are talking about the 100,000 people. Pumping station and distribution reservoir are operated in the conjunction with each other. Pumping station usually pump the average daily demand to distribution reservoir during the minimum demand hours of the day. It means this meet the fluctuation that is the water tank. Elevated tank, you see that. Maybe you can see around your surfaces. Elevated tank circular cross-section cylinder gives a maximum volume. You see that. Elevated tanks. Buried reservoir. That one is rectangular cross-section, generally easy to construct. Cylindrical reservoir, reinforced concrete or steel. A film layer of the about 1 meter thick is placed. Lower temperature is summer. Better storage to meet our following components. That is the other design elements, the pipes. The advantage of the pipes, the mostly used in the water distribution network, resistant to the corrosion, long service life, or 40 or 60 years, easy installation, effective in the landsliding zone, light, resistant to the consolidation and impact. Disadvantages, concrete pipes are used in the free surface transmission line, reinforced concrete pipes are used for the pressure flow, resistant to the corrosion, low cost compared with disadvantage, might expand, might burn, laid below the frost line, although the thermal capacity and the latent heat of the water are so great that there is a little danger of freezing as long as the water remains in motion. According to İlbank, the İlbank is the regulation community in Turkey to dissolve the elevation of 2,050 millimeter than 80 and 100 millimeter are not recommended to determine the appropriate pipe diameter, keeping in mind that it must be bigger than the above values. First of all, flow rate is calculated. First of all, we have to find the flow rate for the water transmission line. For the gravitational transmission pipe, pipe diameter is determined according to existing head. If the calculated diameter does not exist commercially, next bigger pipe diameter is chosen. Why do we say that? This is the order of the calculation. First of all, we determine the flow rate using the population, using the unit discharge, available or not. It is not available, we can choose the commercial one. Velocity limits in the water transmission line pipes. Velocity values in this pipe should be high enough to prevent settling of the suspended solids. The critical value of the achieving this is approximately 0.6 meter per second. At the same time, the velocity should be small to avoid internal corrosion of the pipe. And the critical value is achieving this is 1.8 meter per second. Actually, my friend, these values can be changed according to the type of pipes. But in the exam, in the problem, we will give the minimum and the maximum range of the meter per second. You see that. If we design the water transmission line, okay, you see the cross section of the transmission line. Line 1, if the transmission line is placed parallel to the surface of the ground, it will be as irregular as the ground surface. For each lowest and the highest point of this transmission line, we have for the highest point, we have an air relief valve, and the lowest point, we have a blow-off valve. Okay, that is the alignment, this is the component of the pipe. Why do we put this alignment? Because when we design the water transmission line, approximately this line can lay 2 km, 1 km, 2.5 cooling pressure, and we have the blow-off valve for the times V square over D 2G times L, okay? That is the continuous energy losses. In a long transmission lines, local energy losses are neglected. If you remember for the hydraulic, we have two kinds of energy losses. The one is the local head losses, the other one is the friction or continuous head losses. In general, for the water transmission line, we can use the continuous energy losses. If you design the system according to Manning and Strickler equation, you can use this formula, okay? You can calculate the Manning velocity 1 over n, r over n, these formulas. We have a r is the hydraulic radius is the ratio of the channels head losses. One important note to calculate these formulas, we have a r is the hydraulic radius is the ratio of the channels cross-sectional area the area is the wetted area, that is the red line is the wetted perimeter. So hydraulic radius can be calculated A over P. For the circular pipe, R is the A over U, area of the perimeter. The area is the PD square over 4. The perimeter is the B times T. So for the circular pipe flow, hydraulic radius is equal to D over 4. Do not forget it, my friend. And one more thing, for the energy and the piezometric and the pressure head, if you remember, the Bernoulli equation states that for the constant flow and energy balance between two pipes, cross-section can be written as, that one is the geometrical head, pressure head, and the velocity head in any 2 point is similar for the Bernoulli equation. But for the energy equation, we can add the head losses. That one is the 0.1, that one is the 0.2. 0.1 energy is equal to 0.2 energy plus head losses. So we can draw the hydraulic grade line, energy grade line. You see that, okay? Hydraulic grade line, we call the HGL, avoiding having the hydraulic grade line below the point in the system for which it's plotted to the negative pressure. Okay? Hydraulic grade line and the energy grade line shows the energy point or piezometric grade line points in each point in the system. Okay? Hydraulic grade line shows the P over gamma plus Z. Energy grade line or piezometric grade line shows the P. Okay. air relief valve. If you remember the components of the pipes, we have an air relief valve. That means that is the air pocket. Okay, that is the pipe flow. So for the highest point, the air bubbles can occur. So air release from the water and trapped at high points reduce air bubbles or air mechanical energy to the potential energy in series having a radial flow characteristic are adopted. And one more component is blow-off valve. The blow-off, it should be located at the lowest points at the water transmission line to drain out of the water in case in an emergency, in case. Yes, one of my friends say there is no sound. Okay. The other component is pressure decrease room. We call the PDR. According to the type of the pipe and the pipe connection, there is an allowable maximum pressure inside to the water transmission line. Okay, there is no limitation. We have there is, if the above circumstances are not obtained, pressure is decreased to the atmospheric pressure using the pressure decrease rule. In the free surface flow, like in the PDRs, outlet pipe must be right below the. You want to transmit the water from this reservoir according to type of pipe, and this we will give the different of the valve or 150 meter. It can be changed from water transmission line to the another water transmission line. And the valves, you see that this is the different of the valve. And finally, you should see the cross section of the water transmission line. Okay, profile of the pipeline showing the pipe thickness and the location of the gates, blow off and air valve. Okay, that is our sources. That is our water transmission line. We put the blow off valve, air relief valve, blow off, air relief valve, and then that is the hydraulic grade line. That is the static grade line, and these are the different. These are the length of the pipe of the stationing of the line. Similarly, this is the details of the water transmission line, and that is the design of the transmission line. You can calculate the head loss using the Weisswey equation. And one more thing. Again, that is the reservoir. And that is the hydraulic grade line, static pressure. That is the maybe we can observe maximum pressure in the pipeline in the lowest point. You have to check that point. Okay, if you exceed the maximum pressure, you have to use the pressure decrease room to reduce the pressure. Okay, my friend, actually this is enough for today. We can continue the design of the transmission line next week. Okay, from so far, do you have any question? Actually, this is the introduction, beginning of the designing of the water transmission line. We talk about groundwater. Next week, inshallah, we will solve the problem about the groundwater and the beginning of the water transmission line. Any question, my friend, for today? Okay.
Next week. Thank you very much, Doctor. Have a nice evening.
Next week. Okay.